Hello everyone, and welcome to this feedback on the advanced use of two key Snowflake features, MV, Materialized Views, and DT, Dynamic Tables. My name is Nicolas Corchia. I am CEO of Indexima, and I have been passionate about data for over 10 years, expert in machine learning and BI. The agenda for this presentation is in three parts. First, an introduction to the principles of aggregation in Dataviz. In the second part, we'll focus together on materialized views and dynamic tables in a customer context based on real cases. And finally, we'll look at how to make the most of MVs and DTs once we've seen how the two compare. First, let's talk Dataviz. We'll start to discuss a postulate which is as follows. In order to have a performant BI, especially on big data, we need pre-aggregation. Why are we convinced at Indexima that we need pre-aggregation? Our end user, the one who consumes dashboards, absolutely doesn't want to have to wait for SQL queries to run for dozens of seconds before getting the results of their analyses. As you all know, a BI dashboard is made up of different graphical elements. Each of these graphical elements corresponds to a SQL query, a group by query. This is known as an aggregation query. The result of each of these queries will be read by a human being. So the result of each of these queries is actually small data. This means that whatever the size of the raw data below, the human being using BI is going to read small data. With the increasing volume of data, scaling the compute to calculate aggregates over and over is not cost relevant. That's why we can start from the postulate that in order to perform BI on big data, we'll always perform pre-aggregation. This pre-aggregation consists of keeping the results of queries that are in fact combinations of keys and aggregates. These combinations correspond to recurring questions. For example, give me my sales by quarter and region. There are various ways of storing these aggregations, storing these combinations of keys and aggregates. On top of your raw data, you can implement old-fashioned BI with cubes, extracts, data marts, which will be stored in databases and built manually by teams of data engineers. You can also turn to more recent standards such as hyperindexes or dynamic tables, which will also end up on top of your raw data. Finally, you can, and we're going to work on this, you can work on materialized views, which will be present inside your raw data. These new standards are much more in memory, much more reactive and automated than our cubes, extracts, and data marts when it comes to old-fashioned BI. Today, we're going to focus on two of these new standards, DT, Dynamic Tables, and MV, Materialized Views. Let's start with the definitions. First, MV, Materialized Views. These have been available since November 2018 for premium accounts. In fact, they're simply views. But those views, rather than calculated on the fly, are materialized at creation. The results are calculated and materialized in the database. This ensures the best execution performance. One of the magical things about MVs is that they are automatically maintained by Snowflake. This means that when you ask a question to an MV, you always get the same result as if you'd asked the question to the source table. Another magic of the MV is that you actually ask the question to the table, and Snowflake will take the question to the MV to obtain the best performance. Here's an example of SQL used to create a materialized view. It's quite simple. As you can see, is the result of a select on a table. Now for dynamic tables. From an SQL concept point of view, it's not that far off, but it's important to understand that here we're no longer dealing with a view of a single table, but rather the result of a set of modifications of a data flow that may involve several tables. This stream is automatically kept up to date by Snow's internal processes. There's some magic here too. Here's a definition for creating a DT, a dynamic table. And we notice the appearance of two parameters, the warehouse, which will be used to compute the various operations of this stream, and the target lag. Target lag is a kind of guarantee that Snowflake provides to ensure that your DT will never be off by more than a few hours, here 4, from your source tables. The Snowflake teams have already written an article comparing DTs and MVs. I invite you to have a look. What we're going to do together over the next half hour is share with you some case studies, examples of what we've seen on MVs and DTs by working on real-life use cases, beyond documentation and what can be found there. The feedback we offer you will revolve around different comparison criteria between MVs and DTs: performance, automatic query redirection, data freshness, cost control, and last but not least, are there any SQL limitations to MVs or DTs? The first focus will therefore be on performance. The initial reason for aggregation in BI is to get small data on top of our big data, and for simple mathematical reasons, it's to get good performance by reducing the number of bytes scanned. So, to explain the performance results I'm about to share with you, I'm going to explain a little about our testing process. So what are we talking about? We're talking about tests that run on over 1,000 different SQL query patterns. We didn't invent these SQL queries. They come from our customers. Customers from the energy, finance, IoT, retail, travel, and other sectors. And these customers use Dataviz tools ranging from Tableau and Power BI to BO, Jaspersoft, and others. The data we work with is obviously not our customers' data, but synthetic data set reproducing our customers' dataset volume, cardinalities, and skew. This data is contained in tables ranging from a few million rows to several billion rows. Our tests are always running on warehouses of comparable size, in this case extra small. And these tests have now been running for just over a year, so we're fairly confident in their results. So here you have a table of performance measurements. You have columns and rows. The rows show the use cases. Use case 1 is finance. Use case 2 is retail, and so on. In the columns, the measurements, response times of these use cases. In the finance use case, the first line, you have around 50 queries that were executed in series, which lasted, without MV and without DT, 54 seconds. 2 minutes 38 for the retail queries on line 2, etc. In column 2, the same queries executed in the same way, also sent in series, on a Snowflake containing materialized views. On use case 1, for example, these materialized views made it possible to reduce by a third the execution time of this use case. We went from 54 seconds to 35 seconds. The third column are the dynamic tables, and we can see, for example, that on the first use case, we divide by 2 again. We're down to 17 seconds of execution time on the same queries with the same data. But instead of defining MVs, we defined DTs. If we take a closer look at these different figures, we can see that at MV level, we have acceleration and performance factors ranging from 1 to 80. Look at the fourth line, from 8 minutes to 6 seconds. On the DTs, it's a similar story. We go from 1 to 7 and up to 80. In concrete terms, if we look at the multiplier factors for all our test use cases, we're at times 9 when MVs are added, times 13 when we add DTs. That's quite a performance, quite an acceleration factor. So we can say that we're happy and that these are great acceleration factors. Now, let's be a little critical. Why is it that on some lines we're only at times 1 and on others we're at times 80? Well, I can already tell you that it has nothing to do with the domain. I'm going to have retail use cases that will be greatly accelerated and retail use cases that won't be accelerated. Nor is it related to the size of the initial data. It has much more to do with the complexity of what's going on in the dashboards. Does the dashboard aggregate a lot? Is the MV or DT much smaller than the initial data? Or are there a lot of crossovers leading to a MV or DT that isn't all that small? As a result, performance is degraded. Now perhaps something surprises you. Why does my green accelerate less than my yellow? It surprised us at first. Well, actually, there's a very simple mathematical reason behind it. Within each MV you create, Snowflake adds the partition name. It's written in the documentation. Why do they add the partition name? Simply to enable efficient incremental refresh and better manage what they do very well. Handle the behind by. We'll talk about the behind by later when we discuss data refresh and data freshness. In concrete terms, putting the partition name in the MV has an impact because it makes the MV bigger. You add a new column, a column with cardinalities, and these cardinalities multiply the number of lines, the number of physical rows in your materialization. So you scan more data than in a DT without this partition name, and therefore you won't go as fast. quite simply. Now, despite those limitations, we have very good performance whether we use MVs or DTs on our use cases. We're doing times 9 or times 13, which is great. Now that we've talked about performance, let's talk about the second axis, automatic redirection. In concrete terms, what is automatic redirection? When I send an SQL query to my table, does this query necessarily descend into the table's fine-grained data, or is it automatically redirected by Snowflake to the best aggregation structure? For dynamic tables, this feature is not supported. If you want to use a DT, you need to explicitly target this DT in your SQL query. For MV, the answer is in the documentation. Snowflake's Query Optimizer, the tool inside Snowflake that decides the execution plan for your query, will automatically redirect your query to the best MV to answer it. That's the theory, at least. The reality is that, as we've seen from the various use cases I've presented to you, that in many cases, let's even say in most cases, in the end, it's not the best MV that's chosen, or even no MV is identified at all. For example, here we have an implicit cast that prevents Snowflake Optimizer from using our MV. Now that I've explained that, it's important to return to the table I showed you just before. Remember, we had a first column with the Snowflake reference, a second one with the MV, and a third with the DT, each with acceleration factors. To be totally transparent with you, the columns MV and DT are columns where we ourselves decided which MV to go through, which DT to go through. The column called MV is actually redirected MV. If we hadn't redirected the MV manually, this is how it looks. In fact, the standalone MVs are the response time measurements of these same use cases without telling Snowflake which MV to use. Here, it's a bit disappointing on some use cases, and we're down to an acceleration factor of times 0.9. That is, we've slightly degraded performance, so we can't use this. I have no doubt that the Snowflake teams are already working on improving these factors. If we have to draw a conclusion in terms of MV, if we don't redirect manually on MV, we've found that the rules for identifying an MV that the Query Optimizer will accept and use are actually quite difficult to reverse engineer, and that in fact performance can be worse if there is no manual redirection to MV. One thing you can't see on these graphs, but we've seen it too on MVs, when an MV has not yet been updated, in other words, you update your table, and then the MV layer above has not yet had time to be recalculated. One of Snowflake's magic features is that if I don't yet have the information in the MV, Snowflake will look for it in the source table. Finally, we have this partition column that has just added it to the MV, and this results in a behind by that's not at 0. In other words, your MV is slightly offset from the table. No problem. Don't worry. The query will still get the right result. Our tests have shown, although I don't have any presentable figures yet, that execution performance was further slowed down when the behind by is not at 0. It's logical. When the MV is not yet updated and you have to fetch a bit of information from the MV and a bit of information from the table, it's even slower. Here's where we stand on performance and redirection of MVs. Finally, the results on this second axis of analysis shows that automatic redirect does not exist on DTs, and that we hope that the Snow roadmap will soon improve automatic redirect on MVs. Now let's talk about data freshness. The functional question is there a difference between the data in my table and the data in my aggregation layer? Or, put another way, when I send an SQL query, will I get the same response if I query DT1, DT2, MV1, MV2, or my source table? You could also call it data consistency. As for MVs, once again, Snowflake's documentation is crystal clear. SQL queries executed on MV will all have the exact same answer as calling the source table directly. It's this behind by management thing, the MV column that happens to be the partition name, that's added to keep the link between MV partitions and source table. It doesn't matter what you do, and it doesn't matter what the state of your MV is. No matter what modifications have been made to the table, a query executed on an MV will always return the same response as a query executed on the table. And that's also what we've seen on the various months of use of MVs. On that note, I say well done Snowflake, because it's a great challenge. Now, let's talk about dynamic tables. As I said earlier, what is a dynamic table? Well, it's the result of a stream, so it's multi-table. And then there's a contract between you and Snowflake called target lag. With this contract, Snowflake guarantees that your dynamic table is never delayed more than the target lag. Snow's interface is superb in this respect. It's easy to see here, in my example, the 22 refreshes were executed between September 5th and September 6th. And you can see various columns indicating refresh lag, current lag, etc. So the information is very clear and easy to find. There's a lag, and Snow does its best and does it very well to ensure that the lag is never greater than this target lag. Now, once we're aligned on the fact that the lag for each dynamic table is respected, the question of data consistency remains. Imagine, for example, you have a table on top of which you have a stream that we'll call DT1, and you have another stream that we'll call DT2. Even if the target lags are aligned, Snow can't guarantee that when you send a request to DT1 or DT2 or the source table, you'll get the same response. Snow assures you that the offsets won't be greater than target lag, but the query that runs on DT1, DT2 or source table may have differences, since we have still a lag. This can be annoying. In real life, this is an issue that can be circumvented, thanks to another Snowflake feature we haven't talked about here, but which you're bound to be familiar with: time travel. In fact, we can envision a system in which the timestamp of the least fresh DT is fetched and added to each SQL query, with a time shift pointing to this timestamp. Data freshness, whether on the source table or on the DT, is automatically ensured. The bottom line on this comparison criteria is that on the MV it's really totally transparent. It works really well. On the DT, it all depends on your data update process, whether you update every 5 minutes or every 12 hours, your target leg and the number of dates you have. But there is a risk that aggregated queries targeting a DT won't provide same figures as detailed queries on the source table. Cost control is a very important and interesting topic. The question here is, but how much does it cost me to update a DT? How much does it cost to update a MV? Once again, a test protocol to explain before going any further. We're using a fully automated test protocol, which has been running for a few months on the DTs. The DTs haven't been around for very long. They've been available since July 2023. The MV has been running for a little longer. This test protocol is based on transaction and sales data from retail market. There are 1 billion rows in the fact table at the start of the process. We use a denormalized, flattened model to be able to compare MV and DT. As you may know, MVs cannot work on joins. We'll talk about it later. The DT do support joins, but we're on a denormalized model to be able to make comparisons. The queries we use are reporting type queries, of course, where we query the amount sold per point of sale, or average amount grouped by customer, a kind of average basket. For warehouse size, we're working on extra small. Updates are an important part of this. How do we update this transaction data? We update 1.5 million lines every day of testing. Then we work on cadences. You'll see that there are 3 use cases. One where we update very quickly, one use case we update a little less quickly, and one use case we update a lot less. In parallel with these updates, so that MV and DT are sufficiently sheltered, we have a usage of around 1,500 requests per day. Let's go into the details of the use case 1. So we're in a use case with near real-time insertion. What we call real-time here is that we're going to insert several thousand lines per minute. That's what we call real-time in our case, and we've flagged our dynamic table target lag at 6 hours. Another curve. I love graphs and curves. What do we see on this curve? The number of credits consumed over time, either by dynamic table in blue or by the materialized view in orange, throughout this process, which is both an update process and a consumption process. Calculations show that the MV over this period for this update costs 4 credits. These credits will in fact be found in materialized view maintenance credit. This is a specific area of Snowflake. We see something else too. As you've probably noticed, the orange curve looks erratic. In any case, it's clearly not stable. In blue, the cost of dynamic table, the cumulative figure is 0.5 credits, that is 8 times less, with one very stable credit consumption running on the warehouse defined when the dynamic table was created. It can be followed very closely. Use case 1 gives us a conclusion of 4 credits for MVs, 0.5 credits for DTs. You know what? I've got a use case 2 where we update the data much less frequently. We're no longer in real time, but rather in daily. On the other hand, we have accelerated, we've reduced the target lag of the DTs, we've reduced it to 10 minutes. In this type of use case, once again with the same updates, that is, I have a cumulative daily total of 1.5 million updated lines on top of 1 billion lines in the table initially. My MVs will cost 0.1 credit to update. My DTs will cost about the same, 0.15 credits to update. Finally, the use case 3 reversed the story. I put myself on a real-time insertion in the table, so I'm back to updating every minute, and then I set the target lag to 10 minutes. Here, the MV will cost less than the DT. The MV will cost 4 credits, whereas the DT will cost 8. On the DT side, the calculations are actually quite easy to do, since it's very easy to do the math. Since I have a target lag of 6 hours or 10 minutes, I know every day how much my DT will be updated, and I know how much an update request costs, since I can track them in the warehouse. Whereas on the MV side, well, for real, without having run this test multiple times, I'm totally unable to tell you in advance whether it's going to cost 1 credit, 2 credits, 3 credits, 4 credits, 0.1 credit. As a result, our conclusion to date is to observe that, in fact, they can't be predicted. And in addition to not being predictable, these MV refresh costs cannot be shared with warehouse consumption. Coming back to what I was saying earlier, the dynamic table is going to be updated on the compute of the warehouse you defined when you created the dynamic table. You can define a warehouse dedicated to updating dynamic tables, but you can also share the compute warehouse of your dynamic table with the usage warehouse, in which case the credits will end up being mutualized with consumer credit consumption. On the MV side, we're talking about a dedicated cost that looks a little like cloud compute. And here, you can't mutualize this compute cost with a warehouse that would otherwise be switched on because it's being used for consumption. The cost of updating MVs is isolated and cannot be controlled. You can't increase the power of the warehouse on which you update the MV, and you can't choose a warehouse on which to update the MV. So, from a cost control point of view, we have on the left something which is very difficult to predict and which cannot be shared. On the right, something that's totally predictive, very pragmatic, and what's more, completely mutualizable with the rest of compute usage on your Snowflake warehouses. Last comparison factor. Are there SQL limitations for dynamic table and materialized view? These two features bring a lot to the table, especially in terms of performance, but do they have SQL limitations? Once again, Snowflake's documentation is very clear. There are limitations on the creation of MVs, and these are numerous. You can't make an MV on a join. There's no time travel on the MV. You can't create a group by having no approx count. Distinct window functions are forbidden, etc. So for the time being, there are a lot of limitations on MVs. I have no doubt that Snowflake is working on removing some of them in the months to come. As for DTs, DTs are ultimately streams whose refresh is automated. You can do anything in a stream, so you can do anything in a dynamic table. Here, on this analysis axis, many limitations on the MV side, no limitations on the DT side. If you try to align and wrap up on everything we've just said, we have MVs, first line, DTs, second line, and then axes of reading criteria of comparison. In terms of performance, if we put aside the problem of automatic redirection, whether it's MV or DT, it does the job. We're achieving factors greater than 10 on our test use cases. In terms of data freshness, data consistency, MV is unbeatable, beyond reproach. For the DT, depending on your use case, if you have data that is refreshed regularly, if you have many DTs, if you need to have very up-to-date data, the DT will need to be associated with time travel feature to achieve data consistency. Cost control. We've just talked about cost control which is very difficult to predict on the MV side, very easy to control on the DT side, thanks in particular to this target lag parameter, automatic redirection, that is mandatory, to automatically accelerate queries without rewriting your boards. On the MV side, the promise is there, but the implementation is not yet there. On the DT side, there's no such thing as automatic redirection. And finally, we've just been talking about restrictions, SQL limitations. MV have a lot of them, while DTs don't. That's a very analytical reading of 5 criteria. If we try to take stock of all this, what does this mean for the analyst and for your use cases? To date, the Indexima team recommends that you use MV if the most important thing for you is data consistency and a very fast refresh of your data. If, on the other hand, what's important to you is to control the cost, to handle advanced SQL complexities such as joins, and ensure the best performance, then you'll need to switch to dynamic tables. Now, you'll have to go further if you want it all. That is, if you want both dynamic table performance, all the SQL complexity, the joins, approx, count, distinct, and so on, that can be found in dynamic tables. And the cost control of dynamic tables associated with data consistency of MVs, at that point, you're going to need a solution that helps you go further. You saw me coming. This is why we're talking today. Not that we only have things to say about what's going on in Snowflake with DT and MV, but we also have some things to tell you about how to go even further, thanks in particular to the features we'll find in DTs by associating these DTs with a technology. This technology is Indexima. Indexima will help you to compensate for the shortcomings of dynamic table, namely data freshness and automatic redirection. Indexima, combined with dynamic table, will help you to go even further while relying on dynamic table features. So, how do you go about it? We're no magicians, but let's take a look together. How do we complete those 2 challenges? So, Indexima Query Engine is going to extend Snowflake Query Engine by adding the ability to identify best suited dynamic table and redirect query automatically. So here you have your dashboard pointing to your Snowflake, and then inside Snowflake you have dynamic tables represented by these little green, red, blue, and gray logos. Quite simply, you're going to change the address of your Snowflake inside your board to go through a proxy. A Snowflake proxy, the Indexima proxy. Indexima will slip between your Dataviz and your Snowflake to play the role of proxy, and above all, play the role of query engine, query routing. This operation is totally transparent. You just change a URL, that's all. No installation, no data copying. We use the same drivers, protocols, and writes. Everything is kept as if you were calling Snowflake directly, but you call Indexima, and Indexima calls Snowflake by putting itself between your Dataviz and your Snowflake. Indexima will intercept SQL queries and redirect them to the right DTs. To the DTs with the best structure to meet your needs with the best performance. Then, to ensure data consistency, as I was saying, we're going to align ourselves with the timestamp of the last refreshed DT. And by aligning with the timestamp of the last DT, we use Snowflake's time travel features to ensure consistency. Any request that passes through Indexima will receive a response that will be consistent, regardless of whether this query target a source table or a DT. So we've just seen that Indexima completes the set of features, all the power delivered by Snowflake's DT. But that's not all. Indexima doesn't just play the role of proxy, substitute, and apply time travel to ensure redirection and consistency. Indexima will also help you to automatically create the best dynamic table layer. Once again, no magic, just the expertise we've been deploying for years on all the SQL engines on the market. In concrete terms, Indexima watches SQL requests between your board and Snowflake. And the Indexima optimization engine will apply its clustering algorithms to build the best aggregation layer. Basically, it will group your SQL queries into packets, a green packet, a red packet, etc. And in front of each of these packets, Indexima will define the best dynamic table to reply very efficiently and effectively to your SQL queries. So the DT for green queries, the DT for red queries, etc. Indexima will create them in your Snowflake. Then Indexima will play the role of proxy and redirect each of your requests to the best DT. So you have an engine that acts both as a proxy and as a data engineer to create automatically the best aggregation layer. So now that you've all understood, there's only one thing left to do to speed up your dashboards, control your costs, and take full advantage of all Snowflake's features and power. Open your dashboard, edit the Snowflake source, and replace the .snowflakecomputing.com with .sf.indexima.io. That's it. That's the only modification you need to make to your dashboards. If you want more information on our product, check out our website indexima.com. Of course, we'll be happy to discuss all this with you, so don't hesitate to contact me by email. Thank you for your attention, and have a nice day.